Okay, so this is just a quick feature demo for the game I've made. I'm not going to go too much into architecture, just so I can keep it short. So if we get started, you can see that it's a grid world, so everything's just divided into 2D array of boxes. If I make a bunch of units, then we can see that they spread out. That's just using a separation force. I don't actually have alignment or cohesion implemented. It turns out they weren't actually necessary, and I talk about that in my discussion as well. So first thing, if we just get a dude to make a path, we can see where he's going. So there's only one node because it is smoothed, so we can also turn on the visualization for that. So if I calculate a path over here, it is just using a greedy best first search, and only orthogonal movement is allowed, so no diagonals. I use that over A star because it ended up in most cases being quicker, and that's also one of the topics of my research. So if we visualize the path smoothing as well, it's basically just projecting two lines from the corners of the first node, and just running a line traversal to see which cells it touches, and if any of them happen to be a wall, then we obviously can't move there. If not, then we can move on to smoothing the next node. So in this case, we'll see it smooths all the way to the end, and our path ends up just being the one final node. So the next thing is I also have time-sliced pathfinding enabled. So if I put a wall over here, you can register a search with a path manager, and until that actually gets completed, then the units will just seek towards wherever the destination is, and once the path is complete, we'll send a message back to the unit's path handler, and then they'll get the proper path put on them. It looks a little something like this. So they'll just seek to where they want to go, and then gradually the paths will come in complete. So the next thing is group pathfinding. So if we get a bunch of units to go towards the same destination, we can see they each get an individual path, but it all goes to the exact same place, and then they end up getting stuck on top of each other until separation can push them apart. But if we turn on the group pathfinding, then we get them to move to a path. We can see they all get assigned a path with an offset, so they all sort of come to a smooth sort of stop. So some techniques will use a follow the leader kind of method where we only actually calculate one path and then everyone else just kind of uses the offset pursuit steering behavior to get there. I haven't done that way because it ended up causing a lot of issues going around corners. So I randomly pick a leader and he calculates his path properly using a proper search. And then I manually assign everyone else a separate path using different cells based on an offset from where they are. So although it looks like everyone does have an individual path, there's only one path that's manually calculated, and the rest just manipulate the individual nodes to take into account the offset from where they were. Okay, so the next thing is a path recovery watchdog. It's a pretty simple, just time-based system. So every time a unit goes towards a new node, he'll calculate how long it should take for him to get there, and if that time passes plus a small buffer, then they'll recalculate the path. So if I put a wall here, and then it kicks in, and they recalculate a path to go the correct way. There are also different kind of path requests and different ways for them to be handled. So if we get a path to just a normal destination, where you can walk through, it's just a normal graph search. But for example, if we want to fetch a path to a building, we can't fetch a path to a building itself because we can't walk there. So we instead get the border cells around the building and we fetch a path to the closest one of those. Another one is if we want to fetch a path to a resource and we don't really know where it is, we just want to fetch a path to the closest resource. Then we can run a Dijkstra search to do that. And that'll just run around from wherever the unit is. And the termination condition for that will be any cell that contains a tree. So that's reasonably slow because obviously we need to just Dijkstra's out until we find it. We can't use a heuristic. But most of the time those searches are pretty small because it's pretty much just between the town hall and the resources themselves. So not overly a big issue. So another thing is different units can define different ways of how they want to interpret the path requests. So for example, if I try and send a worker and a minecart both towards a tree, then only the worker goes there because the worker looks at what's at that destination. There's a tree there, the worker knows what to do with the tree, it can collect resources, whereas the minecart doesn't really care about it because it can't collect resources, so it just chooses to ignore that request. So another thing is we can construct buildings. So I can send a worker over there to go and build it. A little green box indicates that a unit is selected. So if I have nothing selected and I still put down a house, it'll just sit there as a template and nothing will happen. And then another different path request that a unit can do is if he's pathing towards a building that's not constructed, then he'll send himself over there to construct it. So we can also set rally points, which is another way of how those path requests can be interpreted from there. So if I set a rally point to the tree for a worker, then he'll immediately start going over to mine it. Similarly, if I build a minecart and the rally point is set over the resource, then the minecart will just sit there and not do anything. So I also have state machines integrated in here. Each unit has its own state machine and different kind of states associated with a unit type. So for example, a unit can have a move to resource state, and then harvest resource while he's doing the actual harvesting, and then return resource when he comes back. Minecarts also have their own set of states and a pretty special way of interpreting path requests when there's a track involved. So they move significantly faster on tracks. So the way they handle their path requests is to run a limited depth Dijkstra search just to see if there are any minecart tracks around. If they are, then they begin their path search, the second phase of it, from wherever that track is. And they use a special heuristic which highly prioritizes any nodes that have a track in them. So for example, if we fetch a path over here, we can see the path follows pretty closely along the track. So the minecart states are move to deposit box and return to town hall. So the general idea is that you can set up a deposit box near some resources, say if it's far away from your base and you don't want to expand all the way out there, and then you can run a minecart along the track and it'll take care of bringing it from the box back to the town hall. So on top of the normal grid here, we also have another grid, which is a course grid on top of that. And I use that for a few things. So the first thing is for spatial partitioning. So the number in each cell represents how many units are in there. So rather than needing to brute force collision check everything, we can just check for units in the same cell as that unit. So it speeds up things a lot. Before I did it, the game started to lag at about 320-ish units. Now it handles 600 pretty comfortably, so that's pretty awesome. Another thing I use it for is fog of war. So you can only see cells that you've explored, and I just use the course grid cells to partition that area to make it a lot easier and a lot quicker. So if we can see a unit moving forward, you can only see what's actually around him. So as he moves further to the right, then these cells over the left are no longer visible. There's one exception to that. So I do have this idea of some sort of permanent vision. So if I put some resources over here, then we can't see it. And if we move our unit towards it, then they're explored. And once he moves away, you can still see them and they'll stay persistent on the minimap. So that's for neutral things, in this case just resources, but it's just a nice feature because it sort of distinguishes between fog of war of what you can see in your units and neutral sort of landscape factors that you have explored. So another thing I use, not the course grid for, but just the grid in general, is a influence map that I generate. So every time I put down a building, it'll propagate some sort of influence, and there's different influence values associated with different building types. If I wanted to expand it, I'd put units in there as well. But just for the purposes of what I was using it for, it sort of made sense just to make it just buildings. So from that, we can also extract our influence border. So this tells us pretty much where the perimeter of our base is. And that's something that can be used by AI and bots, which is something that's demonstrated in the video I have for that. So one kind of cool thing about all this is it's not calculated every frame. It's just purely event-based. So every time a unit moves, if it has a velocity greater than 0, i.e. it's actually moved, then it sends a message to the world to just update that individual unit. So we're not brute forcing everything every frame and recalculating everything, we're just recalculating what needs to be calculated. And that's the same for Fog of War.